what I'm talking about today is describable but unpredictable, non-natural formalisms in modeling. So basically, how do we do the mathematics of alternatives to methodological naturalism? So first of all, in order to do any sort of demarcation, we have to be able to separate between natural and non-natural causes. Okay, and so if you listen to my first talk, you can understand just how hard that is. Okay? But there is one divide that kind of remains that people have proposed that kind of works, and that is that the divide between natural and non-natural can be given an objective meaning. But the problem is that most people who propose that natural is different than non-natural, they don't often give you a good example why. So if someone says natural means something, well, that must also mean that non-natural means something. So in order for two people to have a conversation, they have to agree on what natural and non-natural is. So there's commonly proposed demarcations, and all of them have had problems. One is that naturalistic objects are observable, but the fact is most of physics is not observable. So they say, okay, well, natural objects have cause-effect structure. The problem is that dualists contend that the spirit does yield effects. Me without a spirit is different than me with a spirit. So there is a cause-effect structure even for non-natural objects. Another one is that natural objects are testable. But testability is simply the other side of a cause-effect structure. If I'm different with a soul than without one, then you could test for however it is that I'm different. So these demarcations between natural and non-natural don't really work. So one demarcation that actually can work, at least to some extent, is computability. And so what I like about it is not only is it a decent demarcation, it's been proposed by several materials themselves. And so basically they say naturalism are computable processes. And so therefore, the converse, they don't really go into supernaturalism, but they say that nature, everything in nature is computable. So we could then take the converse of that and say that non-naturalism or supernaturalism, or however you want to term it, are incomputable processes. So the benefits of this view is that it's unambiguous because the theory of computation is actually very well established. It matches our intuitive concepts about natural and non-natural, and it has adherence from both materialists and non-materialists. Okay, so not everyone likes this demarcation, but contrary to every other attempt to demarcate it, it actually you can actually do a demarcation on it. So so methodological naturalism, if it has any meaning today, indicates that the behavior of objects occur in a calculable manner. One of the goals of alternatives to methodological naturalism would be to incorporate less well-behaved functions into models of explanation. So to give you an idea of what this is, we're going to do a little brief history of math. This is not a perfect history. I'm not a math history guy, but this is kind of just give you a feel for it. So growth in number types, we started with the natural numbers. Then we expand that to the integers. Then you have the rational numbers, 1/3, 2/3, 3/5. Then you have the real numbers, which include the irrationals like the square root of 2 and all those. Then you have the complex numbers where you have the complex unit I, which is the square root of -1. And then on top of that, you have the hyperreal numbers, which include infinitesimals and infinities. And the hyperreal numbers have only really been investigated in the last 100 or so years. And really as a number system, it's really been fairly recently. And then we have the growth of function theory. Okay, so it started out just being the concept of independent and dependent quantities. Then we talk about differentiable functions. Then we have multivariable and implicit functions. Then we have the separation of the function and its representation. So we can have a function even if we don't have an equation for it. Then you have partial functions. And then you have generalized functions and multivalued functions. So you kind of, concept of what a function is and what qualifies as a function keeps expanding to more and more, it starts out with things that are very concrete and solid, like your typical, algebra type math, and it grows and grows until you have things that are hardly recognizable as functions, which we'll see some of those. And then we have the growth of analytic operators and functions. So you start out with arithmetic, and then you get exponentiation, you get the trigonometric functions, the logarithmic functions, you get infinite series. So there's a lot of functions that can be represented by infinite series. The hyperbolic functions, number theoretic operators, we'll look at a few of those, and then Weierstrass's monsters, which are very cool but very odd. So the takeaway from history is that on the tail end of mathematical theory, there's a number of aspects of mathematics that are hard. And by hard, I don't mean difficult to grasp. I mean that the computation required for the calculation does not scale linearly with where you are on the graph. So if you go, like when I was talking about number theoretic operators, this is like decomposing a large number into primes. Okay, that is a hard problem. The entire security of the internet is based on the fact that that's a hard problem. They're unpredictable, so you cannot deduce the behavior of f of x at x either from the definition of the function or from prior values of the function. I mean, kind of in a sense you can, but it's not like if I have a straight line, right, and I know what it means to be a straight line, and I have a point that's near the point that I want to look at, I can predict the behavior of that next point from the previous point. Okay, and that's true of most of our commonly thought of functions. In calculable, the behavior of f of x at x cannot necessarily be fully calculated from the definition of f of x in a finite number of steps. We'll get to talking about a halting problem and other things. And then indeterminate, so the behavior of f of x is not fully specified by the equation. So, even if something is hard, unpredictable, and incalculable, it may only have one answer. But then we also have functions that are indeterminate. They might have more than one answer at a given position. And so the functions themselves do not fully articulate what's going on. So most people grow up on well-behaved mathematical functions. And the other types of functions are either unknown or they're viewed more as a curiosity. So, one of the things that I kind of want to promote is that people who are interested in alternatives to methodological naturalism investigate some of these newer mathematics because they're very, very interesting. Computation theory especially. I don't know if Paul's on for this one, but he was talking about his investigation that he wants to do. I think computation theory is just ripe with all sorts of investigative tools that can be used. Non-standard analysis is the way to view infinities and infinitesimals. And I actually tried to get a guy on to do a talk on infinities and infinitesimals at this conference, but he wound up, I think he was too ill to actually, he's an older guy, and I think he was not up to doing a conference. But when you think about things that are infinities, we're really talking about things that are not describable under naturalism. You don't have infinities of things under naturalism. So I'm thinking about how other modes of causation might impact mathematical models. Okay, so I just want to give you some examples of strange functions. Okay, because I kind of talk about them a lot, but you may not be familiar with what they are. Here's some normal functions. Okay, and so what I mean by normal function is that if I take an arbitrarily small section of any of these, even the ones that curve and go up and down, if I can actually take a derivative at a single point, and if I get enough of them, I can extrapolate what that curve is going to do pretty much all the way out. Okay, so I can calculate future cases derived from an extremely small sample space. Okay, so and so this is kind of the types of functions that people are used to using in physics is functions like this, functions where you can extrapolate what it's going to do based on, physics, you usually have, if you're dropping balls and you extrapolate that to, how how the Earth works and how pebbles work, you've got quite a range there that you're inferring from simple experiments, and the ability to infer those quantitatively stem from the fact that these are very typical functions. Okay, so the next function I'm showing you is a random function using von Mises' definition of random, and it's random between 0 and 100. And so interesting thing about von Mises random functions is that let's see what my time is. Okay, all infinite subsets of this have the same probability distribution. Okay, now it's recursively definable infinite subsets have the same probability distribution. That's one of the requirements for von Mises random functions. The result at any point is not dependent on the x value at all. The prediction based on previous values is not possible, although generalized prediction is possible because we can know what the distribution is if this is a random function. So you move from being able to predict specific things to be able to predict distributions of things. Okay, and randomness is kind of my switching point where I think randomness counts as a non-naturalistic cause if you really think about it, but it's one that's been accepted into physics, and so it makes a good bouncing point for including others. So you can kind of look at how the methodology for including randomness affects things, and then you can then move that on to more interesting functions. I think the reason why they allowed randomness is because randomness is not, at least doesn't sound teleological. I actually believe that in some cases it can be, but nonetheless, that's the reason why randomness got kind of a special pass was because it was thought of as being inherently ateleological. So here's another function, distinct prime factors, and you'll notice that the distribution is not regular. It's actually very irregular. So the computational complexity increases with each additional number. It does not linearly increase. It increases in complexity. I didn't actually work out what the actual computational complexity was, but and an interesting thing about this is that if you view it as a causal principle, the causation is not uniform. Okay, so some items are caused by things right by so many behind them, and others are caused by a longer string of things behind them. So if you think about like the number 2, since 2 is a prime factor and it's a prime factor for every even number, it has an inordinate causal power in this list of distinct prime factors, whereas 3 has slightly less, and 5 has even less. But on any given number, knowing how much causation is being involved is actually very difficult. And so as opposed to kind of the normal functions where you can say, okay, well, we can infer where the next point is based on the very previous point. You can't do that here. And then now the interesting thing is bounds are computable from primes. I can find what the, if between 2 and 6, you only have at most 2 distinct prime factors. But between 2 and 1,000, you have a lot more. All right, so the bounds are computable, but not the actual values. In fact, technically, not even the distribution. So, so you have, what you can see is that you have these functions where there are true things that you can find out about them, but they aren't necessarily the same true things that you're used to finding out. Okay? Goldbach partition function kind of runs along the same way. This is the number of ways a number can be added from prime add-ins. The Cantor function is very interesting. It's technically considered a continuous function. I am not sure if it's continuous over the hyperreals or not, but it's continuous over the real values. But despite being continuous, it actually has the derivative almost everywhere is 0. And then the only place where it actually has one, it's infinite. I believe it's infinite. I'd have to double check that. But so rarely it's considered measure zero across the function. So the Cantor function is built by interval halving. So what that means is that we take 2 points and we take the middle third of it and color it in at the halfway point. And so the interesting thing is that the causation actually happens from two different sides. So you have forward causation and backwards causation, and it fills in, right? So that's a really interesting notion of causation that doesn't match our typical notions of what a function is or how it should work. The halting function, given a number, which computer programs can be represented as numbers, on a machine, does the number represent a halting program, one that actually finishes, not gives you a little spinny? It's incomputable in the general case, and it requires an infinite amount of computation time, a literal infinite amount of computation time to determine a zero in the general case. And many number theoretic functions can be represented in terms of the halting problem. So now how do we make use of these strange functions? So we now understand that there's functions that don't represent causality in the way that we're used to seeing them. So how do we make use of them? Okay. Well, why do we use mathematics at all? Well, mathematics forces us to be rigorous in our thinking. Being rigorous allows us to make formal logical inferences. And without formalisms, rigorous inferences are difficult, or they can often become imprecise. And then historically, naturalism has caused us to desire the predictability and inferability of normal functions. And I'm running short on time. I'll see what I can do. So strange functions allow us to make formal statements about the affairs of the world which don't follow the presuppositions of naturalism. So randomness, as I said, is a kind of a stepping stone. So quantum mechanics is predictive, but includes a random component which isn't. So quantum mechanics states bounds, but not results. Einstein actually viewed this as not being, not in the same terminology, but he basically viewed this as not being methodologically naturalistic because there was a cause that wasn't given by previous conditions, which is Laplace's definition of mechanical philosophy. The randomness does not prevent knowledge building. It just changes the type of knowledge that results. And so we shouldn't assume that reality must conform to just popular notions on causation. So another example is a Turing oracle. And a Turing oracle is a machine, it's a symbolic representation of a machine that can exist. Okay, it yields a problematic answer, like one that for an incomputable or hard function in one step. Their original usage was with the halting problem. The halting oracle gives the answer to a halting problem in one step. So as I said, it doesn't exist, but it's a way of thinking about it. And so, but they allow us a broader conception of non-material processes. Allows operations to be represented even if they can't be computed. And since they have solid definitions, they can be used to reason about functions even if their actual function can't be predicted. So for example, Turing used oracles to show relative complexities of different functions. So he said, even if I could have an oracle, I still can't quite achieve this level of functional complexity. So he was able to use it in reasoning, even though he couldn't use it in computation. So, and then my own, this is from the book Engineering in the Ultimate, and this is an Axiom oracle for describing insight. And basically what I said is, so I is what I call the insight function. So given a decision problem like the halting problem, you're given a program, an input to it, basically all the things that you need, and you have a set of axioms, but you're missing one. Insight can provide the missing axiom. And so basically it says insight is the process of generating a new needed axiom, and says it needs, where am I in time? Okay, it needs all axioms plus one, plus a problem on which the axiom could be used. So if you think about it, that's the way insight works. If I'm stumped and there's one thing that I need, oftentimes you have insight to provide that missing axiom to move forward. So it's not perfect. I still have not fully formalized the meaning of axiom in this case, and I'm working on it, but it's slow. But it does match the process of insight and describes it in a more formal way than before. And it can be used to model and formalize how insight leads to growth of knowledge generally. So we can say, running against this problem yields this insight, or running into this problem, insight leads to this new axiom, which then can be applied to this range of problems, which goes to this problem, which requires an insight to generate a new axiom, which leads to the solution of this range of problems. So you can see how it can be descriptive, even if it isn't predictive, and it can help us understand the world. But that leads to the notion of testability. So one of the core concepts of science is exposing theories to test. Because testing forces us to rethink our theories. It's not an absolute truth teller, but we can get hints when we're going the wrong direction, kind of a sanity check. So science tests, basically finding, it's kind of a short-circuited philosophical method. For example, the identity of the indiscernibles, say if the two things are exactly equal in all of its qualities, then they are the same. Okay, well the science, in a lab, we can't test all of the properties of something, so I find key qualities that I think are important and test those. Okay, so it's kind of a truncated version of philosophical reasoning. Let's see here. Now, all scientific theories are underdetermined by the data, so that's important. So tests cannot exclusively point to a scientific theory anyway, and all data has error, and so we need to keep those in mind. So how do we test? If a function is non-computable, how do we test it? Well, even if functions are not calculable, they do exhibit relationships. So you can find features and patterns of these relationships that are uncommon elsewhere, and then check the patterns in actuality. And this level of testing is at least as strong as that proposed by Ernst Mayr for the testing of evolutionary biology. So as an example, randomness will be kind of our stepping stone. Random events follow a Poisson distribution, and I actually I'm not good at pronouncing foreign words, sorry. So in such a distribution, mean equals the variance, okay? So therefore, in lots of experimental sciences, these distributions are tested just by checking whether the mean equals the variance. There are other ways, other than this distribution, that mean can equal variance. But having the model predict that and then discovering the relationship to be true is considered valid evidence of that distribution. So our randomness, we have a non-mechanical process. It's non-predictive, only knowable by relationships, underdetermined by data. But we have a feature that it's not unique for that distribution, but it is common with that distribution and uncommon elsewhere. And we can use that for testing non-mechanical processes. So kind of to wrap up, mathematics allows the definition of functions which can be described but not calculated, and therefore they can't be predicted. And using such functions allows us to formalize non-calculable notions of causation. Such formulations do not prevent inferences in knowledge building, but they sometimes limit the types of inferences that can be drawn. So if you're going to do this kind of modeling, you need to have formal reasons for believing causation to be structured in whatever way you're proposing, right? So you can't just pull a distribution out of the air. You have to say, okay, well, it matches this sort of cause. Okay? Then you have to have a way to check the results of known values in relationships against of the relationships caused by your model against the empirically determined ones. And you should also, though, also as well give room for error, which is probably doing giving error bars in this kind of analysis is probably worth its own discussion. But ultimately, and this is true even in naturalistic science, the final decision of which model is best is and has always been a philosophical one. Models are underdetermined by data. Therefore, the choice of which one always has to be philosophical. All right, so I'm now going to open it up to questions. Let's see if yeah, you all should be able to talk. So any questions?
Hey, Jonathan, this is Jim Johansson. I liked your talk and kind of interesting to think this through a little bit. One of the things that I think you mentioned was one of the ways to go between natural and supernatural is whether something is computational, that would be something that would be in the natural, and something that's supernatural that is non-computational. So I want to make sure I understood that correct. Is that true?
Yeah, that's exactly where I'm drawing it. I give a more comprehensive defense of that in my book Engineering in the Ultimate. So
okay, yeah.
That's not technically my book. It's a conference proceedings of the last Blythe Institute conference. And so, but I had some papers in there, and it explains more in depth why I think that's a good dividing point. But I think
I think that sounds fine. The one thing I wanted to what I'm beginning to think about is just to give you a mental picture. You probably saw the movie Interstellar, and it talks about.
I haven't actually.
Well, it talks about. Yeah, well, I'll just describe it briefly. It talks about, they come to this, black hole, and there's something called the event horizon, where once you go past that, you can't get out. So you're quote, looking into something that you can't quite really understand what it is. What happens when you get into those things when you're having to deal with infinite quantities, infinite power or something like that? In mathematics, there's ways that you can begin to sort of have a, limiting case where you can sort of, like the delta function. There's ways that you can represent these mathematical oddities, and you can actually, to go beyond you can't, quote, compute it, but you can at least bound it. And it seems like there's a way that where in our being finite, we can still reach a little bit further into the infinite. What I would argue is a distinction between what we can know in the natural world versus what is in the supernatural world. And maybe that's a useful thing to consider when we get into that transitional area where it's not always clear how far you can go. But if you can start to come up with some of those limiting presumptions, then maybe you can go just a little bit further and understand a little bit more. So that maybe I have a thought on that, but that's one of my premises I'm trying to explore.
I think that's a really good point. I think that's that's one of the things that I'm hoping to accomplish is just to get everyone to take another step out, go a little bit further, go a little bit beyond where they're comfortable with, and I teach a homeschool calculus course, and my goal in teaching calculus is not necessarily the getting people to actually know the specifics of calculus, but I try to get them to be able to understand and think about things in new ways. So, for example, we're going over Taylor and Maclaurin series, and so the way I introduced it is, I've been talking to them for a while about integrals that don't have solutions, and so I talked about how if you have the integral of the sine of x squared, right? There's no solution for it. It's impossible to determine. Okay, and then I said, and next week we're going to determine it, and then I showed that the statement that it's not determinable is actually true, but there are extra clauses you have to add in there. It's not determinable with a finite number of elementary functions. If you remove the restriction of finite number of elementary functions, then you can determine it. You can determine it with an infinite series. You can represent the sine of x squared as an infinite power series, and then you can integrate the series term. And so just kind of to help them understand that there are boundaries. But sometimes the boundaries, and the boundaries are good. There's nothing wrong with them. With the boundary of a finite number of elementary functions, we were able to do a lot of math. I think the Risch algorithm, to some extent, comes from that. But without, but it's also good to know that you can also step beyond those boundaries if you're willing to throw off some assumptions that you might not have been willing to otherwise.